Professor.
All right. Hello, everyone.
Hello.
Well,
That homework took me 12 hours to do, and I didn't
What?
finish. That homework took me 12 hours to do, and I didn't finish it.
Took you 12 hours and you didn't finish it?
Yep.
Wow. Okay. Well, let me just set something up here. Okay. Now let's share this device to my laptop. Start now. It's the end of the world as we know it. So I was playing that song because, you know, I look out the window.
I knew that as soon as I signed up for your class.
What?
I knew it was the end of the world as soon as I signed up for your class.
Say that one more time.
I knew it was the end of the world as soon as I signed up for your class.
So I'm not playing the song for that reason. I'm playing the song because, you know, I look outside and the skies are dark and it's raining ash and there's, you know, a deadly disease rampaging and periodically riots in the streets and unemployment. And yeah, you know, it just kind of seems that way. But I want to explain why it is, in terms of physics, that the sky looks so dark right now. So I'm going to share my screen. All right. So I'm going to take 5 minutes to do this before the main class time starts. So let's say you got a bunch of light traveling and it encounters a particle. Well, this light has an intensity, I of x, where x is the distance horizontally, and there's a bunch of particles. And so one thing we could ask is, how does the intensity of the light change as the light propagates? So what we're really asking is, in this case, how does the intensity of the direct beam change? Okay, light hits a particle, the light doesn't necessarily go away, but it scatters out of the direct beam. It changes direction. So we're just asking right now about direct beam. Well, the rate at which it changes has got to be negative. The direct beam is getting weaker. It's got to be proportional to the intensity of the direct beam. The more light there is, the more that can be scattered out. It's got to be proportional to the number of particles per unit volume. The more particles there are, the more it's going to attenuate. And then it's proportional to something called sigma, which is a cross section. And it's called a cross section because let's just look at units. This is intensity over length. Derivative of intensity with respect to x is intensity over length. This is intensity. So all of this has to have units of 1 over length. Now, n over v has units of 1 over length cubed, which means we better be able to multiply by something with units of length squared, so we just get 1 over length. And that cross section, well, this constant here, there's got to be some kind of constant that's going to depend on how strongly the particles scatter. That's got to have units of length squared, and length squared is area, hence we call it a cross section. And it turns out that if we plot the cross section divided by, if we just look at circular particles, and many particles can be approximated as circular, and we plot cross section versus circle radius, and then the cross section is proportional to r to the 6th. I feel like I'm missing something. The scattering, the efficiency is, yeah, okay, r to the 6th. It's r to the 6th. So initially it's r to the sixth. And then later on, it kind of slows down and just becomes r squared. So for very small particles, it's proportional to r to the sixth, because it turns out that we can write pi by dz as equal to the volume of the particle squared over the wavelength of light to the fourth. Right? That's a fact I'm not going to derive because we've only got a minute or two. And so what that means is that for small particle size, because then there's the intensity, because we've got this volume squared over lambda to the fourth, sigma is proportional to 1 over lambda to the fourth. So for really short wavelengths, like blue light, we get lots and lots of scattering, okay? So blue light leaves the beam, and that is why the sky is blue. But red light stays in the beam. So we got red and blue coming in. Blue light mostly leaves the beam. Red mostly stays in the beam. And that is why for very small particles, that's why for scattering by very small particles, you're left with red light. That's why the sky is blue. And that's also why the sunset is so red, because let me do this. Blue. All right, at sunset, we are here at sunset. Okay, we're standing right here, we're revolving that way. Probably getting some detail wrong right now. But at sunset, if we look at the atmosphere as being this blanket around us, all right, at noon, the sunset just goes like this. It goes straight through the atmosphere. But at sunset, it goes through a much thicker section of the atmosphere. Because it's thicker, there's more scattering. And so at sunset, more blue light has been scattered out, and you're left just with red. Now here's the final fact I want to explain: post-apocalyptic hellscape that is outside my window right now, which is, I said that the derivative of intensity is proportional to intensity times number of particles per volume times a cross section. Well, let's see here. And when I look at that post-apocalyptic hellscape, I see that there's roughly 1 particle per 2 meters, okay? The particles are a couple meters apart. So it would be, each particle would be in a cube of volume 2 by 2 by 2. So 1 over 8 cubic meters. Okay, or roughly 10 to the minus 1 meters to the negative 3. And the cross section for large particles becomes comparable to the area. And some of the ash that I see in the sky is about 1 centimeter. So it's going to be 10 to the minus 2 meters, whole thing squared, or 10 to the minus 4 meters. And actually, it's more like apart. So it's going to be roughly just 1 per 1 meter squared, or just 1 meter to the negative 3rd. And so what I've got is that sigma times n over v is roughly 10 to the minus 4 meters to the negative 1, or 1 over all of that is roughly 10 to the 4th meters, is roughly 10 kilometers. Now, when I look out my window, where I live, there's a range of hills just a mile or 2 away, and then there's the mountains when I look north. And the hills a mile or 2 away, I can see. The mountains, which are 10 miles away, I can't see. And sure enough, the average distance that a photon travels before getting scattered is roughly 10 kilometers or several miles. And so this explains why I can see the hills that are about 1 mile away, but not the mountain range further in the distance. Any questions on the appearance of the post-apocalyptic hellscape that we live in?
Nothing. It's terrifying.
Yeah, there's a whole lot that's terrifying right now. But you know, that's great. It also
Some results from a search.
and now for some reason when I put my tablet into screen sharing mode, it becomes super helpful and constantly tries to share information with me. Okay. There's something in the chat. How long will the end last? Oh, that all depends on which end time prophecy you believe. According to J.R.R. Tolkien in the Silmarillion, Morgoth will escape from his banishment outside the door of night and return, but then he will be defeated by Tulkas, Eonwë, and Turin. So, yeah, we don't know. Okay. Yes, I'm a big Tolkien geek. What I'm going to do now is I'm going to pose a question to you. Let me look at my list of polling questions. All right, you should see a poll right now. Which problem from problem set 3 should I go over? Since I am told that that was a difficult problem set, I will go over one of the problems that was due this morning. For those who came in late, the reason why we're talking about post-apocalyptic hellscape is not so that I can rant about the world going to hell in a handbasket. I do that every day. It's because the appearance of the sky enables me to, or serves as a useful segue for a little lecture on light scattering. Okay, so take another 20 seconds for more people to vote. Okay, looks like the most popular one is question 6. Let's take a look at question 6. The force from an infinite surface. Now this is based on something that we did in class last time. Okay, so we've got a particle that is a distance h above a surface. And we want to find the energy. And we know that the potential energy is minus sigma dA. If I just look at...
Dr. Small, we can't see the iPad you're writing on.
Oh, okay. Can you see it now?
Yeah.
Okay, so we got a particle at distance h over this, h above the surface. And the potential energy is minus sigma dA over this distance s to the n power. Now, s is the square root of r squared plus h squared, if we're working in polar coordinates on the surface. And dA is r dr d phi. And I could rewrite this as r squared plus h squared to the 1/2. So what we're left with, this would just be du. This would just be one little contribution to the potential energy of this particle.
I'm sorry, Dr. Small. Just for clarification, are we doing a disk or are we doing an infinite sheet?
Well, an infinite disk and an infinite sheet are the same thing once they're infinite, right?
Yeah. No, you're right. Okay.
Okay. So we get minus sigma times the integral from phi equals 0 to 2 pi and from r equals 0 to infinity of r dr d phi over r squared plus h squared to the n over 2. All right, the d phi, when we integrate over this, we're going to get 2 pi. We're going to get 2 pi from that integral. And if we say that u is r squared plus h squared, then du is going to be 2r dr. And so we're left with minus pi sigma integral from from u is now at its lower bound. When r is 0, u is h squared. And when r is infinity, u is infinity. So we get, and then we get the 2, we took out the pi, the 2r dr is du. So we get du over u to the n over 2.
Quick question.
Yes.
So that substitution for u, specifically r squared is equal to u.
R squared is equal to u?
Yeah, that's what I was looking over your lecture notes, and that's what I saw. So there's my point of confusion.
R squared plus h squared is equal to u.
Okay, so it's just a simple u sub. All right.
Yes, it's a u substitution.
So then the question is, how can you go from dr squared, right, and then say that
dr
is
squared? Where did I write dr squared?
in the not here in the lecture notes from last Wednesday? You said dr squared or 2r dr is equal to dr squared, which is equal to d and then that u sub that you have on your paper right there. How did you make those relationships?
I don't. If I had said the change in r squared, all right, that might have been, I might have, and this is just a guess. I don't have last Wednesday's notes in front of me right now. It might have been r plus dr squared minus r squared. This is a guess as to last week. This is from last week, since I got a question about last week. This is not what I'm writing to solve this problem. So that would be r squared plus 2r dr plus the little dr squared minus r squared. This is tiny, so we ignore it. These cancel, and we're left with 2r dr. It is possible that that's what I said, but here's a little tip for you, Sebastian. Here's a great time to ask me questions about last week's lecture. Office hours after last week's lecture, not during this week's topic.
Okay.
I'm saying that we should never, ever go over old things, but in the middle of a derivation to suddenly try to do a gotcha on last week's lecture. Any questions about what I'm doing here?
No.
All right, not hearing any. So we have to integrate u to the 1 over u to the n over 2. I could rewrite this as minus pi sigma integral from h squared to infinity of u to the minus n over 2 du, which gives us minus pi sigma 1 over minus n over 2 plus 1 u to the minus n over 2 plus 1, because it's just like any other power, h squared to infinity all right, now what? Now what we do is we have, well, let's see here. Infinity to some negative power is 0, minus h squared to the n over 2, sorry, negative n over 2 plus 1. And what we're left with is this minus sign and that minus sign cancel. And so we're left with pi sigma over 1 minus n over 2 times h squared times minus n over 2 times h squared, or pi sigma over 1 minus n over 2 times h to the 2 minus n. And that's if we just have the particle interacting with an infinite sheet. Any questions on that?
Yeah, on the homework, did we, would it be wrong to specify if that n can't equal 2?
Yeah, that's fine. That was sort of an implicit assumption. It's fine to state that. N actually can equal 2, but then we get a logarithm. And as long as, because if n is 2, then we've got the negative 2 over 2 power, the negative 1 power, and the integral of the negative 1 power is actually a logarithm. But yeah, that's. Any other questions? Well, then I say let's go a little bit further. I say let's replace this infinite and thin sheet with something of finite thickness dz. Let's integrate.
Wait, Professor?
Yeah.
Wait, I thought you also had to do the force or find the force for part
The
A.
force is the derivative with respect to h.
Oh, so it's not respect to S then.
The
A.
force from one little infinitesimal element would be the derivative with respect to s, yes. But when we've got a whole bunch of pieces, some of them pulling this way, some of them pulling that way. And so because some of them are pulling down and to the right, and some of them are pulling down and to the left, the end result is that they're just pulling down. And that comes from taking the derivative.
Okay, thank you.
So now we could replace this with this problem. So now we have to integrate, we have to add up all of those potentials from z equals h to infinity. Because of course, in this case, the potential is just 1 over, it's just h to the 2 minus n. But if it's down here, the potential is, if it's a distance z in, then it's going to be 1 over, it's going to be some constants times 1 over h plus z to the n minus 2 dz. And we have to add up over all of those. Any questions?
Yes, another question on the previous part, just real quick.
Yeah.
Because on my homework, so I got exactly what you got, except I stated that if n, like, do we have to state like some sort of a situation for n? Because I noticed that if n is greater than 2, then that negative in the exponent would be bigger, and it would bring the infinity to the denominator. Can we say that it goes to 0 if it's greater than, or that the potential energy goes to negative infinity if n is less than 2, and it goes to what we have here if it's greater than 2?
Yeah, that's fine. I mean, that's what you just said is true. I'm implicitly assuming a fairly large value of n. I should have made that more explicit in the problem.
Okay.
But yeah, you can freely assume that n has some value that will make this work. In practice, when I wrote this problem, I was thinking of van der Waals forces, not to be confused with van der Voort forces. Van der Waals forces are the forces that act between electrically neutral molecules. If you have two molecules that have no net electric charge and they aren't spontaneously polarized, then they still attract each other. And these forces are tremendously important in biology and chemistry. And those potentials, usually at least for short distances, go as 1 over s to the 6th. And for somewhat larger distances, they go as 1 over s to the 7th. And so the forces go as 1 over s to the 7th or 1 over s to the 8th because you take the derivative.
Thank you, Professor.
All right, let's move on. We're going to talk about vectors. I hope that this is mostly review. Vectors are, of course, quantities that have both a length and a direction. And wow, it is dark in here. Normally when I'm up here at 10:20 in the morning, it is quite bright with the orientation of my windows. But yeah, it is dark in the path of, well, we're pretty far from the fire, but we're in the path of the ash blowing. All right, so, excuse me, I'm gonna get at least a little bit of light on. Okay, I'm back. So vectors are quantities that have a length and a direction. And there are a whole bunch of notations. And part of what you have to learn in math, I wish that everybody did math in the same notation, just like I wish that everybody on Earth spoke the same language and made the same assumptions that I make. But that's not the world we live in. So you will see some people say that the length of A is this, an absolute value sign around A. Others will say just A without the arrow over it. You'll see both. Some people will write a vector like this in terms of its components, AX, AY, AZ. Some people will write it as a row vector like that, or as a column vector. When we get to linear algebra next week and start doing things with matrices, we're going to tend to use column vectors. But that is equivalent to what I think is a more convenient way of writing things out if you're not multiplying by matrices, which is to say AX times a unit vector in the X direction plus AY times a unit vector in the Y direction plus AZ times a unit vector in the Z direction. Not everybody calls their unit vectors X hat, Y hat, and Z hat. You will see E hat X, E hat Y, E hat Z. E hat is a common notation for a unit vector because E comes from the German word for one, which I think is ein. You will see, God help us, I hat, J hat, and K hat. I hate that notation because I is the square root of -1, J is an index, and K is a wave number, but you will see people do that. You will see E hat 1, E hat 2, and E hat 3. They are all used. But however people write these things, the length of a vector is just given by the Pythagorean theorem. So if, for instance, A was equal to 3x hat plus 4y hat plus 12z hat, then the length of A would be the square root of 3 squared plus 4 squared plus 12 squared, or the square root of 9 plus 16 plus 144, or the square root of 169, or 13. I tend to use Pythagorean triples for a lot of vector problems because lengths are easy. Any questions on that so far? Well, those are pretty common facts, but something that sometimes gets people a little more confused is they say, okay, so if I've got a vector whose components were just written as numbers, then yeah, I use the Pythagorean theorem. But what if like the vector like is like a bunch like of other symbols like? Then what do we do? What if it was V naught cosine omega t, omega t x hat plus V naught sine omega t y hat minus gt z hat. This is something that could certainly come up in next semester's mechanics class. I often get the question, so do I just like take like the square root like of all like the components like squared and then like added? Yes. If a vector is written in terms of symbols instead of numbers, you do everything exactly the same as you would with numbers. Symbols are just substitutes for numbers. We don't have one kind of trigonometry for numbers and another kind of trigonometry for symbols. So it would be V naught squared cos squared omega t plus V naught squared sine squared omega t plus g squared t squared. And whenever you see something like this, your instinct should be crying out to replace that with just V naught squared, because cos squared plus sine squared is 1. And some people say, okay, so like cos squared theta plus sine squared theta is 1. But what about like cos squared of something complicated like omega t like? Is like the cos squared of like a complicated thing plus like the sine squared like of like a complicated thing also still like 1 like? Yes. Cos squared plus sine squared is 1, period. There's no special trigonometry. It's not like there's high school trigonometry, well, God help us in our fallen era, college trigonometry, and then later on physics trigonometry. There's trigonometry. I'm going over these things now because I'm really hoping that by the time you're in mechanics, you won't have to deal with this pain. A thing that's a little more subtle, and here's where I think the question is a fair one, is scalar multiplication and complex numbers. Can we multiply a vector by a complex number? And the answer is we absolutely can. Just like we can multiply a vector by any other number. If I have some scalar s, s could be 1, 2, 3.1415926. It could be -5. It could be -1 billion. It could be 2 plus 17i. It could be anything. S times a is just equal to s times ax, x hat, plus s times ay, y hat, plus s times az, z hat. And by the way, I will almost always use x hat, y hat, and z hat because I think it communicates most clearly what direction is what, but you will see other conventions and you'll just have to get used to them. Just like if someday you should ever decide that you don't like dry weather and you go to the East Coast, you will learn that they don't say the in front of the freeway number. They don't say we're going to take the 95 from DC to New York. They'll say we're going to take 95, when any good right-thinking Californian would say we're going to take the 5 to Northern California. Not 5, the 5. And on a more serious note, a lot of this is just linguistic convention. In certain branches of physics, there are even jokes about how you can tell whether someone went to grad school on the East Coast or the West Coast based on their notation. Because, you know, why would you ask them what the name of a freeway is when you could just ask them how they write down the metric tensor in general relativity? But this does lead to some issues if I want to take the length of a vector multiplied by a complex scalar. And the honest answer here is that as soon as somebody starts expressing physical quantities with real numbers, you have to ask them, what are they really trying to convey? And usually what they're trying to convey is that the thing that they actually want to measure is the real part of S times A. And if all they want is the real part of S times A, if that's the thing that they're actually going to measure in the lab, then you could just say, okay, well, the length of the real part of S times A is just the square root of the real part of S times AX squared plus the real part of S times AY squared plus the real part of S times AZ squared. If that's what they want, if that's the actual quantity that they're talking about, then work with that. Then that's what you would do. You would find the length of the actual quantity that they're talking about. But oftentimes in physics, people don't take the real part until the absolute last possible moment of a calculation. So sometimes they just want the length of S times A, which is just the absolute value of S times the length of A. It all depends on what they actually want. Now let me give you an example here. Suppose that I have a magnetic field given by B naught e to the I omega t x hat plus I B naught e to the I omega t y hat. The real part of B, well, let's see here. I've got, let's assume B naught is real for simplicity. X hat is real by definition. So I've got e to the I omega t times x hat. The only real thing, e to the I omega t is cosine omega t plus I sine omega t. The I sine certainly isn't real. So I've got b naught cosine omega t x hat. And then I've got I times this complex exponential. Now I times cosine omega t is, well, imaginary. But I times I sine omega t is real because I times I is -1. So I get minus b naught sine omega t y hat. And then the length of the real part of b is just b naught square root of cos squared omega t plus sine squared omega t, or b naught. And strictly speaking, I should be saying absolute value of b naught, because b naught might be negative, who knows. Any questions so far?
I have a question, Professor.
What?
Are we allowed?
I can't
Are
hear
we
you.
allowed to?
You're gonna have
Oh,
to speak
I'm
up because
quiet.
I've got a weird setting on my computer when I'm sharing between two devices. And so all the
Okay.
sound gets really faint. So try one more time.
Are we allowed to exchange the absolute value and real operators? Like, could we do real of the absolute value versus the absolute value of the real?
No, and here's why. Because the absolute value, the question is, do the real and absolute value operators commute? So let's see here. Let's take the real part of the absolute value of I. What's the absolute value of I?
It's 1. I see how this is not going to work. Thank you.
Yep. Whereas the absolute value of the real part of I, the real part of I is 0. So you've got the absolute value of 0, which is 0. So no, good question. Now, I'm not going to do too much of this, but you should know that if somebody wanted to work with this expression, this complex expression, and only worry about real things at the very, very end, if we took the absolute value of B, not the absolute value of the real part, just the absolute value, we would get the absolute value of B naught, the absolute value of e to the I omega t times the square root of 1 squared plus 1 squared. Because when we factor all that out, we've got x hat plus y hat. And that would be absolute value of B naught root 2, which certainly doesn't look like what we had up here. That's one of the reasons why people have to be careful. Everything I'm telling you right now, don't worry. I'm not going to put these subtleties of complex vectors and real parts on a test. This is something you should practice if you take, say, a more theory-oriented class in electromagnetic waves where this stuff does come up. But I want you to be aware of it. On the other hand, oftentimes what people care about is not the length of a vector, but the squared length, because the squared length of a vector is often used in energy. For instance, kinetic energy is 1/2 m length of v squared. So if the squared length is useful, then what people might really care about is 1/2 times the complex conjugate of B dotted with B. And we'll go over dot products more rigorously later today, but hopefully you recall at least the basic idea. So what we're going to have is 1/2 times B naught squared times e to the minus I omega t x hat plus negative I, because we're taking a complex conjugate, e to the minus I omega t y hat dotted with e to the I omega t x hat plus I e to the I omega t y hat. Now when I dot these two, e to the minus I omega t, e to the plus I omega t, I get 1. So I get 1/2 B naught squared times 1 plus, and then I've got minus I times I, that's 1, and e to the minus I omega t, e to the plus I omega t, that's 1. And we just get B naught squared. So there's a lot of intricacies to this complex notation. I'm not going to go through all of the stuff with complex vectors today, but if you read through more advanced books on electromagnetic waves, you will often come across people writing expressions that you had previously just seen as a squared length, saying things like 1/2 E star dotted with E, or 1/2 the real part of E star dotted with H, or 1/2 the real part of E star cross H. And that's where a lot of these 1/2s and complex conjugates are coming from. They're coming from the fact that if you were to take a real part, the thing that you actually measure, you'd only be getting one part of a two-part expression. But if you take the entire expression rather than just one part of it, then you might have to, and actually these are not good examples of it, never mind, let's focus on something like this. If we took the real part and squared it, we'd be squaring just one part of a two-part expression. If I take the whole expression and square it, oftentimes those two parts are redundant once squared, and hence we have the 1/2 to compensate for that. That's why in a lot of more advanced books on waves, you'll see expressions like this. If you take nothing else away, take away that everything from, let's say here to here is not on the test. It's just for your acculturation, much like my discussion earlier of why the sky looks red and why the mean free path of light traveling through this post-apocalyptic hellscape is such that I can see hills a mile or two away, but not hills 10 miles away. So it's kind of nice where I live that I can basically look at different landmarks and measure the mean free path of light in the time of low air quality by just seeing which landmark is visible, which landmark is not visible. That cutoff is roughly the mean free path of a photon bouncing around. And I can estimate it by just saying how far apart are the little flecks of ash raining down from the sky. And yes, I worked a lot on light scattering in grad school. I remember once, I finally figured out fog and why it is. I remember when I finally understood why it is that as I walk through fog, it's not like I ever catch up with the fog. You know, you see clearly in front of you and fuzzy stuff in the distance, and you can never catch up with the fuzzy stuff. And once I understood mean free paths, I'm like, oh, that's why I can't catch up with the fog. Okay, so I've been doing a lot of things. Let's just, let me give you something to think about. Do you see this question on the screen in front of you?
Yes.
I see it, yes.
Okay, slideshow from current slide. Oh wait, you probably see my next slide.
Yep.
We didn't see it at first, though.
Okay, so I had to swap those two views. All right, maybe some of you didn't notice. Anyway, try actually doing the calculation and then vote on it. So try actually doing the calculation. Let's take another 30 seconds. All right, there was a question in the chat. Can a response be revised? I don't think there's a way to do it, but I'll just make a mental note of that. All right. Is there anyone else who wants to vote in the next 10 seconds, or should we just close this exam? I'm going to close this example in 10 seconds, so. Okay. The most popular answer is 3 or 5, and the next most popular answer is 5 or 7, which is not at all a confusing way to state math. So let's look at the solution. We've got 3.5 x hat plus 3.5 y hat minus 0.5 x hat minus negative 0.5 y hat, or 3x hat plus 4y hat. I think the most common mistake, the reason why some people were picking 7, is because you thought that length is just the x component plus the y component, or the absolute value of the x component plus the absolute value of the y component. For geometry, that is wrong. Now, there are cases in linear algebra where you define something called a vector space, which has properties similar to the geometry of our usual three-dimensional space. And one can have vector spaces where we calculate lengths in different ways. And these things are actually really important in data analysis, but they are not at all used in the actual geometry of three-dimensional space. In the geometry of three-dimensional space, the length of this vector is 5 because we use the Pythagorean theorem. There are cases in data analysis where we don't use the Pythagorean theorem. There's cases in something called calculus of variations, where you're doing calculus on spaces of functions instead of calculus on functions of variables, where you use something called the infinity norm. But that's not this. Any questions on this case? All right, let me point out one more thing about vectors. Vector equations are actually multiple equations. To wit, if I say that P is equal to Q E delta T minus mg y hat delta T, something that might show up in a mechanics equation, that momentum is equal to electric force multiplied by time interval plus gravitational force. And you're thinking, wait, plus gravitational force? Well, yeah, the gravitational force is something pointing in the minus y direction. That would mean that Px is equal to Qex delta T, Py is Qey delta T, and Pz is Qez delta T minus mg, oh, sorry. The mg delta t should go on the y component, all right? This is 3 equations in one. That's part of why we use vector notation, because vector notation is a way to compactly write down in one line things that are actually happening in 3 different directions, and to just state the basic physical fact of motion. Another fact that's worth noting is so far I've been doing everything in x, y, and z coordinates. There's no rule that we have to pick those 3 axes. People pick all sorts of axes. Someone, if we just stick to 2D for ease of illustration, might prefer coordinate system. This should be a y. Like this, that's been rotated through an angle theta. A perfectly good reason to do that would be if you've got motion along an inclined plane. Then you would say that your x hat prime would be, well, let's see, this x hat prime has a y component, which is sine of theta, plus x hat cosine theta. And then this y hat prime, well, let's see here, it has a y component that is sine of theta plus 90 degrees times y hat plus cosine of theta plus 90 degrees times x hat, or sine of 90 minus negative theta y hat plus cosine of 90 minus negative theta x hat, which is cosine of negative theta y hat plus sine of negative theta x hat. And there could be lots of other directions that we might choose. People will routinely, you could take any vector and make a unit vector out of it. If I've got a vector C, I can construct C hat equals C over, let me erase that. C over the length of C, and that's a unit vector because the length of C hat is just the length of C over the length of C. So as long as C wasn't a 0 vector, I've got 1. And sometimes people want things like that. For instance, suppose that I've set up some complicated experiment in a lab, in some elaborate geometry, where I've got an electric field acting in this direction. There's any number of reasons why I could have an experiment with things in an electric field. You might want to do measurements along that electric field and measurements perpendicular to that electric field. If the z, let's say for the sake of argument that the z direction is perpendicular to the electric field, then I could have my 3 basis vectors. Basis vector just being a word for the vectors defining my 3 coordinate axes, the unit vectors pointing in the 3 coordinate directions. Well, one of them might be E hat, where E hat would just be the electric field divided by its magnitude. That might be a direction I want to work on because I've set up an experiment where a lot of motion is happening along the direction of that electric field. And then Z hat would be another one. And then I'm just going to call this one U hat for my third unit vector. Somebody in the lab would have to, get out the ruler or protractor and figure out what is the direction perpendicular to E in that plane. But that would be a perfectly fine set of coordinates. People can work in any set of coordinates that they want. Any questions on how I would construct a unit vector? The most important thing for now is that all of our unit vectors are perpendicular to each other. When we get into linear algebra, we'll talk about ways to use non-perpendicular unit vectors. It involves matrices. But for simple geometry, your unit vectors should be perpendicular. That's when the Pythagorean theorem still holds. If your unit vectors aren't perpendicular, Pythagorean theorem no longer holds. If I were to choose 3 unit vectors like this, all bets are off. Pythagorean theorem no longer holds. If I call this A hat, B hat, and C hat, then the length of a vector V is not equal to the square root of V sub A squared plus V sub B squared plus V sub C squared if A hat, B hat, C hat are not perpendicular. If you want to use the Pythagorean theorem, everything has to be perpendicular. Now, there are very good reasons to not use the Pythagorean theorem, to choose a coordinate system that's not perpendicular. Oftentimes, the axes of crystals are not perpendicular to each other. When the axes of crystals aren't perpendicular to each other, then yeah, you have to, if you want to work in that coordinate system, and often you do, then you get an advantage because all of your coordinates are really easy to use. It's really easy to write down the positions of atoms in this coordinate system, but you pay a price. You can't use the Pythagorean theorem. You have to use something more complicated. But of all the alternative coordinate systems, probably the most important alternative coordinate system is polar coordinates. And in polar coordinates, unit vectors get a whole lot more complicated. So we usually write a position in physics as a vector called r. And it's equal to x times x hat plus y times y hat plus z times z hat. And this is already somewhat confusing because x shows up twice. You've got the x coordinate and you've got the x unit vector. So you've got a coordinate x telling you how far you are in the x direction. That's the distance along the x axis. And then you've got this unit vector x hat pointing in the x direction. So the symbol shows up in a few different cases, just like 2, 2, and 2. And depending on what kind of accent you have in some parts of the country, these 3 words are pronounced exactly the same. In other parts of the country, 2 of them are pronounced the same and 1 of them differently. It's similar to Mary, Mary, and Mary. All right. Mary the name, Mary as in marrying someone. and merry as in the happiness. This is just an unavoidable fact. So we normally write positions. This is even before polar coordinates. We normally write positions like this in physics. If I want to say, hey, we're going to measure the electric field at a point R, well, the vector going from, or at a point whose position vector is R, we're at a point in space given by x times x hat plus y times y hat plus z times z hat. But in polar coordinates, and now I'll just stick to 2D, if I'm at a point R, well, what do you think R hat would be, given what I just said about the definition of a unit vector?
It's going to be the vector over its magnitude.
Yep. R hat is R over the length of R. So if R is x hat plus y hat, for now we're just sticking to 2D, R hat is going to be x hat plus y hat over the square root of x squared plus y squared. And the length of the vector R is also called little r. So we've got 3 r's here, just like 2, 2, and 2. And every language has trios of words that are either the same or very, very similar, yet mean very different things. Although you could argue that TOO and TWO basically mean the same thing, the number 2, and then to have this to be like, oh yeah, I got that one too. Well, that means that you also or additionally as one more, and hence the number 2. There's no way around this. This is the language that we use. This is the language used in every book of physics. If I had 6 infinity stones, I would snap my fingers and change the notation and change everyone's memory so that nobody remembers the old notation. I don't have 6 infinity stones, which means that you are just going to have to deal with these. Now this creates a problem. We're used to saying that a vector is that a vector A would be given by AX x hat plus AY y hat. So many people figure that R, what I'm about to write down, is wrong. That R is equal to R times R hat plus phi times phi hat. This is wrong. Please do not confront me next lecture and say, Professor, you wrote that down, but that's wrong. I know it's wrong, right? The vector R hat is a special unit vector. It's defined for that point in space. So if I'm right here, R hat points in that direction. If I was over here, then R hat would point in that direction. If I were over here, R hat would point in that direction. So R hat depends on position. It's different from X hat, okay? No matter where I am in space, if I'm over here, this is X hat. If I'm over here, this is X hat. If I'm way down here, this is X hat. Ditto for Y hat. Y hat is the same everywhere in space. But over here, R hat is pointing this way. Over here, R hat is pointing this way. And over here, R hat is pointing that way. Okay? So R hat is defined as the vector R over its length, which means that the vector R is by definition its length multiplied by R hat. R hat is defined for your position in space. Now, that doesn't mean that phi doesn't come up in polar coordinates. There's still a phi, there's still a phi hat. Here's phi hat. Right? Phi hat at that point in space is defined that way because phi is increasing in that direction. Over here, this is phi hat. Because if I go around that angle, then phi is increasing as I go in that direction. And if I'm over here, this is phi hat because I go all the way around and phi is increasing in that direction. Phi hat points in the direction of increasing phi, right? And phi hat is always perpendicular to r hat. One way to think about why phi hat is perpendicular to r hat is even though I just said that r hat is different at different points in space, let's go out along this line. Along this line, phi is a constant along that line, right? Whether I'm here or here or here, the angle is the same. R is different. R hat is the same. You're going to work through a lot of these things on Friday. Any questions so far? I wish I took this class before mechanics. I see in the chat. Yeah, I'm doing this because I taught mechanics and it was at least as bitter of an experience for me as it was for the students in mechanics. And I'm like, yeah, maybe if they had gone over polar coordinates in detail before mechanics, mechanics would not have, I wish I had taken this class before 4170. There's no such thing as too much math. The answer to, the correct thing to say for any kind of physics is, I wish I had taken more math before I took that physics. I've never heard a physicist say, you know what, I didn't need to learn any more math. I'm good, I'm good. That never comes up. All right, any questions besides just say, oh, I wish I had taken this class before, insert course number here. Any questions on how I do these things? Let's talk about how we would figure out phi hat. R is easy. R hat is just like we said. If I tell you where we are in space, I give you the X and Y coordinates, you can just immediately write down R hat like that. Phi hat. Well, now we have to think about cross products, okay? Because we've really got three dimensions. Even though I've been talking in 2D, it helps to remember that we've got a z-axis coming out of the page. Because I'm going to make the claim that phi hat is equal to z hat cross r hat. I'm going to make that claim, and then I'm going to demonstrate it. So, put your fingers, take your right hand and point your fingers along the direction of out of the page first. Okay, so start off, you've got your notes, you're writing this, you've got your fingers coming out of the page, which is the direction that the z-axis would be. Then curl your fingers on your right hand into the page towards the r hat vector. And your thumb will now be pointing in the direction of increasing phi if you do that correctly. So you draw your axes just like I've drawn them here. X is horizontal, Y is vertical, Z is out of the page. This is r hat. So we start with our fingers pointing out of that page in the direction of Z. We curl them towards R. Our thumb, if you did it correctly, should be pointing in this direction. All right? That's the direction that your thumb should be pointing. And so then we can say that, well, now we have to remember the formula for cross products, which is 3 unit vectors across the top of the page. Then z hat, well, let's see here. If I got a vector that's pointing in the z direction, it has no x or y coordinates, it's z, no x or y components, excuse me. Its z component is 1. And then we've got cosine phi, sine phi, and 0, because we already established that those are the components of r hat. If that wasn't clear, well, let's see, I'll just put phi here. Then the x component has to be cosine phi. The y component has to be sine of phi. And so what we're finally left with is just this. And so the x component will be 0 times 0 minus 1 times sine phi. The y component will be, should be a minus y hat, because it alternates when you go across taking those determinants. 0 times 0 minus 1 times cosine phi. And then the z will have 0 times sine phi, 0 times cosine phi. So we'll just get 0 times z hat. And when we put it all together, we got minus sine phi x hat plus cosine phi times y hat. Any questions so far? So if you remember nothing else, remember that r hat depends on where you are in space. Phi hat depends on where you are in space, and they're perpendicular to each other. Another thing you should know is that even though r is by definition r times r hat, and r is not equal to r hat plus phi hat, I want to make it clear that this is wrong. Some other vector, a could be equal to r hat plus a phi hat. To wit, suppose that I am here, okay? This is r. I've got some vector like this. I'm going to call this a. Well, let's draw our r hat. R hat has to be down and to the right. This is r hat because it's pointing away from the origin at our point in space. Phi hat could either be up and to the right or down and to the left. But let's think. Both of those directions are perpendicular to r hat. But only one of these is in the direction of increasing phi. So this has to be phi hat. Now, when I look at this vector A, does A have a projection onto the radial direction? To the direction away from the origin? Yeah, I can project A onto that direction. So AR is non-zero. And when I look at the phi direction, again, A has a non-zero projection onto this direction. So A sub phi is non-zero. So in general, this is true. Okay, a vector, if I'm standing at some point in space and I want to figure out what are the components of that vector, I can project it onto the radial direction and the phi direction. No problem. There's only a special vector that's not equal to r times r hat plus phi times phi hat. But in general, any other vector could be projected onto both the radial direction and the phi direction. And with that, we're out of time. On Friday, we're going to do some activities involving unit vectors and some polar coordinates. On Monday, I'm going to talk about vector products and a little bit of geometry. And then on Wednesday, we're going to start with linear algebra and matrices. I'll stick around for a few minutes if people have questions, but you're free to go.
Thank you, Dr. Small.
You're welcome.
Thank you, Professor.
You're welcome.
Thanks, Professor. Have a good day.
You too.
Dr. Small, I just have one quick question I wanted to make sure of from something you mentioned earlier.
Yep.
So for when you were saying that if, for example, you want to get, if you want to multiply a, hold on, what was it? A complex scalar by a vector. In the cases where we know eventually we're only going to take the real part, is it always just safe to take the real part at the very beginning and not have to deal with the imaginary part?
Yeah, that would usually be done in situations where the vector is easy to manipulate. The reason why we work with complex vectors in the first place is because we often have a bunch of oscillating functions, and oscillating functions are easier to work with in exponential form. But if you had something that was easier to, exponential form and hence complex form, but if you had something that was easier to just work with as a real number, by all means do that.
Okay, okay. Because it confused me in the book. There was a portion where they would have been able to only deal with the real portion, but they kept the, they included the I term, and it was confusing when they did that.
Where in the book was this? Let me look at the example.
Okay. So it was in the series and limits chapter, page 123 at the very bottom, and then continuing on to 124.
Well, there they wanted the, oh, I see. So they wanted the real part, but they had two choices. They could do a bunch of trig identities. They could figure out the trig identity for cosine 2 theta, the trig identity for the cosine of 3 theta, and so forth. Or they could just use the fact that e to the I theta raised to a power is cosine of that power multiplied by theta.
Yeah, that's what I did.
Okay? And so they could just keep working with powers to avoid having to use trig identities and then take the real part at the very end.
Mm-hmm.
If you have e to the I times a power, the real part of that is the cosine of the power times theta. The imaginary part is the sine of the power times theta.
Right. Okay.
And this way they can turn problems of double angle formulas, triple angle formulas, quadruple angle formulas, etc., into just powers. And powers are much easier to work with.
Right. Okay. But in this specific case, they wouldn't have been able to do anything with trig identities because the only thing you have are sine and cosine. You don't have any powers or anything like that.
They wanted to sum the series cosine theta plus cosine of 2 theta plus cosine of 3 theta plus cosine of 4 theta plus cosine of 5 theta, right?
Right.
Okay. That series, if you just deal with power, summing a series of powers is easy. turning that series into working with the cosine of 2 theta and the cosine of 3 theta and the cosine of 4 theta in terms of trig identities, that's hard. They have no other way to do this. What they recognize is that cosine of 2 theta is the real part of a power. And they know how to sum up a series of powers. That series of powers is really easy. That's why they did that.
Mhm.
I'm not sure, what was it that you're not getting?
You know what? I think, so when I did the problem, I had pretty much everything that they had, but instead of just writing exp for x1, I actually included the e. So it was a lot simpler for me to see when I wrote it myself.
Okay, yeah, they wrote x, whereas you wrote e to the I theta. E to the
Yeah, I guess their notation just confused me a little bit.
Got it.
All right, that was the only thing I wanted to make sure of. Thank you very much, Dr. Smalley. Have a good day.
Welcome.
Bye.
All right. Thea, do you have a question?
No, sorry, just wanted to listen because I was also stuck on some of these for the series, but just because my memory was a little bit fuzzy. But thank you.
You're welcome.